Apollo 11 looks impossible not because it broke the laws of physics, but because it obeyed them with almost zero margin for error. When you understand what actually had to go right, the real mystery isn't how we faked it, it's how we survived it. Before we dive into this topic, make sure to subscribe and comment where in the world you're watching from. When people say the moon landing looks impossible, they're usually dismissed as uninformed or conspiratorial. But that reaction misses something important. That sense of disbelief isn't stupidity, it's intuition. And in this case, intuition is reacting to something real. Apollo 11 should feel unbelievable, not because it violated the laws of physics, but because it pushed them to the absolute edge. In physics, impossible doesn't always mean forbidden. As Michio Kaku often explains, many things that feel impossible are actually just extremely improbable. They sit so far out on the edge of what's technically survivable that our brains reject them as unrealistic. We confuse rarity with impossibility. Think about how we judge events today. We expect progress to be gradual, safer, smarter, more automated over time. We assume earlier technology must have been cruder, slower, less capable. So when we look back at 1969 and see humans leaving Earth, crossing 250,000 miles of empty space, landing on another world and returning alive, something feels wrong. Not because it breaks physics, but because it breaks our modern expectations of how progress is supposed to work. Apollo didn't benefit from comfort, redundancy, or digital intelligence the way modern systems do. It succeeded through precision, planning, and human judgment under extreme constraints. Thousands of things had to go right the first time, often with no backup. That level of perfection feels unnatural to us now. We live in a world where systems fail safely. Apollo lived in a world where failure meant death. This is why disbelief keeps resurfacing generation after generation, not because new evidence appears, but because our distance from that mindset grows. The farther we move from an era that accepted enormous risk in pursuit of singular goals, the more alien Apollo becomes. It stops feeling like history and starts feeling like mythology. This video isn't about mocking skeptics or arguing point by point against conspiracy theories. It's about understanding the psychological and physical reasons why Apollo 11 feels impossible. Because once you understand that feeling, you realize something unsettling. The moon landing doesn't seem fake because it was easy to stage. It seems fake because it was brutally hard to survive. And that discomfort isn't a flaw in the story, it's the point. If you wanted to choose the worst possible moment in human history to attempt a moon landing, 1969 would be near the top of the list. This is what makes Apollo 11 feel so absurd in hindsight. People imagine NASA benefiting from some hidden era of advanced technology. The reality is the opposite. Apollo happened when almost everything about spaceflight was still experimental. The first human spaceflight had occurred less than a decade earlier. Yuri Gagarin orbited Earth in 1961, and even that mission was essentially a controlled survival test. Astronauts didn't yet know how the human body would react to long periods in microgravity, bone loss, muscle atrophy, fluid shifts, radiation exposure. Most of this was still theoretical. Every mission added new data, often by putting lives at risk. Rocket technology was equally immature. Explosions were common. Engines failed. Guidance systems malfunctioned. Even during Apollo, rockets were lost in testing, and astronauts died on the ground. Apollo 1 killed 3 astronauts in a cabin fire during a routine test, a stark reminder that spaceflight wasn't safe even before leaving Earth. And yet, instead of slowing down, NASA doubled down. Then there were the computers. In 1969, computing power was primitive by any modern standard. Computers filled entire rooms, consumed massive amounts of electricity, and had less processing power than a modern digital watch. They couldn't multitask, they couldn't adapt. They executed instructions blindly and crashed if overwhelmed. And these were the machines tasked with navigating humans across 240,000 miles of space. Even communication was fragile. Signals took time to travel. Once astronauts left Earth orbit, real-time control was impossible. There was no rescue mission, no backup crew, no way to send help. If something went wrong, it would unfold far from Earth in silence. And yet this is when humanity decided to try, not to orbit the moon, not to send robots, but to land people on its surface and bring them home. From a historical perspective, it borders on irrational. We weren't ready. The technology wasn't mature. The risks weren't fully understood. That's why Apollo feels impossible. It didn't arrive at the end of a long, safe learning curve. It happened near the beginning. And that makes the decision itself almost as shocking as the achievement. One of the strongest reasons people say the moon landing was impossible comes down to a single question: the computers. When you hear what NASA was working with in 1969, disbelief feels almost rational. The Apollo guidance computer, the most advanced computer ever flown at the time, had about 64 kilobytes of memory. Not megabytes, not gigabytes, kilobytes. That's less computing power than a basic calculator, less than a modern car key, less than the chip inside a cheap toy. And this tiny machine was supposed to guide humans across 240,000 miles of space, land them on another world, and bring them back alive. From a modern perspective, that sounds absurd. Today we rely on massive cloud servers and GPS satellites just to navigate city streets. So how could something so weak possibly handle a mission so complex? The answer is that it was never asked to. The Apollo guidance computer wasn't designed to think. It was designed to execute. As physicist Michio Kaku often points out, Apollo didn't rely on a single supercomputer. Intelligence was distributed. Ground control handled heavy calculations. Astronauts handled judgment and decision-making. The computer handled timing, orientation, and precision. Each part of the system did exactly what it was best at, and nothing more. Most of the complex math was done on Earth using large mainframe computers. Trajectories, engine burns, and correction windows were calculated in advance. Mission control constantly tracked the spacecraft and sent updated instructions to the crew, who manually entered them into the computer. The AGC's job was to carry out those instructions flawlessly, not to improvise. Even the software reflected this philosophy. Every line of code was written by hand, reviewed and optimized down to the last instruction. There was no room for inefficiency. This work was led by Margaret Hamilton, who helped invent the foundations of modern software engineering out of necessity: error handling, task prioritization, and fail-safe design. That discipline saved the mission. During the Apollo 11 landing, when the computer became overloaded, it didn't crash. It dropped non-essential tasks and kept running the critical ones. That decision, made years earlier in software design, kept the lunar module flying. The computer wasn't powerful, it was precise, and in an environment where mistakes are fatal, precision mattered more than raw power. If the computers weren't enough to make Apollo feel impossible, the mathematics should. Getting to the moon wasn't just about pointing a rocket upward and hoping for the best. It required navigating one of the most notoriously difficult problems in physics, the three-body problem. In simple terms, the three-body problem describes what happens when three objects with significant gravity, like Earth, the Moon, and a spacecraft, interact with each other. With two bodies, the math is clean and predictable. Add a third, and the system becomes chaotic. Small changes in position or velocity can grow into massive deviations over time. Even today, there is no general closed-form solution. We rely on numerical simulations run on powerful computers to model these trajectories. Now remember the year 1969. NASA did not have the luxury of real-time simulations or adaptive onboard computing. Instead, engineers relied on pre-computed trajectories calculated on Earth. Using mainframe computers, slide rules, and human intuition, they planned precise burn windows and flight paths that would naturally carry the spacecraft toward the moon. These weren't straight lines. They were carefully curved paths that used gravity as a tool rather than something to fight against. But pre-planning wasn't enough. Once the spacecraft left Earth orbit, tiny errors were inevitable. A slight engine imbalance, a minor timing offset, even venting gas could alter the trajectory. Over hundreds of thousands of miles, those small errors could compound into a complete miss. That's where constant correction came in. Mission Control continuously tracked Apollo using radar and radio signals, calculating its exact position and velocity. When adjustments were needed, they sent correction instructions to the astronauts, who manually entered them into the guidance computer. Navigation also wasn't purely digital. The crew used a sextant to measure angles between stars, Earth, and the Moon, cross-checking their position manually. These techniques echoed ancient maritime navigation, blended with cutting-edge physics. If electronics failed, the astronauts still had a way to know where they were. Apollo didn't solve the three-body problem by overpowering it with computation. It sidestepped it through prediction, simplification, and disciplined execution. The math wasn't conquered, it was managed. That's what makes the mission feel insane in retrospect. Humans crossed a chaotic gravitational system using foresight, correction, and trusting calculations made long before launch. Not because the math was easy, but because it was respected. If there is one aspect of Apollo 11 that truly sounds like a deal breaker, it isn't cameras or computers, it's radiation. Space is not empty in a harmless way. It is flooded with high-energy particles from the Sun, from distant supernovae, and from Earth's own magnetic environment. And humans are not built to withstand prolonged exposure to that kind of radiation. Surrounding Earth are the Van Allen radiation belts, regions where charged particles are trapped by Earth's magnetic field. In some areas, radiation levels are high enough to damage DNA, destroy cells, and dramatically increase cancer risk. On paper, sending humans straight through these belts sounds reckless. The Apollo spacecraft had no thick lead shielding, no heavy protective walls, just thin aluminum. To many people, that alone makes the mission feel impossible. But radiation danger is not just about intensity, it's about dose over time. The Van Allen belts are most dangerous if you stay in them. Apollo didn't. Mission planners designed flight paths that passed through the thinnest regions of the belts at high speed. The astronauts spent roughly an hour total in the most intense radiation zones. Not days, not weeks, about an hour. When scientists calculate the actual dose received by Apollo astronauts, the numbers are surprisingly modest. Depending on the mission, the exposure was comparable to a few medical CT scans, not harmless, but far from lethal. The human body can tolerate short bursts of radiation far better than continuous exposure. The real danger wasn't the belts themselves, it was the Sun. A major solar particle event during the mission could have flooded space with lethal radiation. And here is the uncomfortable truth. Apollo couldn't engineer its way out of that risk. NASA monitored solar activity obsessively and launched only during periods of low solar activity. The missions avoided major solar storms partly because of careful timing and partly because the universe cooperated. By modern standards, this level of risk would be unacceptable. Today, we demand layers of redundancy and wide safety margins. Apollo accepted something else entirely, calculated risk at the edge of survivability. The astronauts knew it. They signed waivers acknowledging they might not return. Radiation didn't make Apollo impossible. It made it dangerous. And the willingness to accept that danger is part of what separates Apollo's era from our own. When people see the lunar module for the first time, disbelief is almost automatic. It doesn't look like a spacecraft. It looks fragile, awkward, almost unfinished. Thin metal panels, exposed wiring, wrinkled foil, spindly legs that seem barely capable of holding anything up. To modern eyes, it looks fake, and that reaction is understandable. We associate safety with strength, thickness, and polish, but physics doesn't care about appearances. The lunar module looked the way it did because it was designed for one environment only, the vacuum of space and the weak gravity of the Moon. It was never meant to fly through Earth's atmosphere. There was no air pressure pushing from the outside, no wind, no aerodynamic stress. Once it left lunar orbit, it would never experience full Earth gravity again. In that context, everything we expect a sturdy vehicle to look like becomes unnecessary weight, and weight was the enemy. Every extra kilogram required more fuel. More fuel required a larger rocket. A larger rocket meant more complexity, more failure points, and a higher chance of catastrophe. So engineers stripped the lunar module down to the the absolute minimum. The walls were just thick enough to hold internal pressure. The structure was just strong enough to function in 1/6 Earth gravity, nothing more. Even the materials confused people. The foil-like exterior wasn't decoration, it was thermal insulation, protecting the crew from temperature swings that ranged from extreme heat to extreme cold. The exposed wiring wasn't sloppy engineering, it was intentional accessibility and mass reduction. The legs weren't built to look reassuring, they were built to absorb impact and keep the module upright on uneven terrain. The design also reflects a crucial fact many people miss. The lunar module didn't need to come home intact. Half of it, the descent stage, was meant to be abandoned on the moon. Only the ascent stage had to lift off and rendezvous with the command module. That single-use design allowed trade-offs that would be unthinkable in an aircraft or reusable spacecraft. As Michio Kaku often emphasizes, nature rewards efficiency, not aesthetics. The lunar module wasn't fragile in context. It was honest, built to do exactly one job in exactly one place with nothing wasted. And that ruthless optimization is why it worked. Apollo 11 did not succeed because everything went according to plan. It succeeded because failure was avoided by the smallest margin imaginable. If there is a moment where the mission truly feels impossible, this is it. As the lunar module Eagle began its descent, almost nothing felt routine. Within moments, the onboard computer started flashing unfamiliar alarms, 1201 and 1202. These were program alarms indicating that the computer was overloaded, trying to process more data than it could handle. In many systems, that would have meant a crash, a frozen display, a complete loss of guidance. If that had happened, the landing would have been aborted instantly. Mission control froze. Engineers scrambled to interpret the alarms in real time. There was no manual for this exact scenario, but the software did something remarkable. It didn't shut down. It discarded low-priority tasks and preserved the critical ones. Navigation and control stayed alive. That behavior wasn't accidental. It was the result of deliberate design choices made years earlier. The computer was allowed to fail gracefully instead of catastrophically. That decision alone kept the mission alive. Then came the terrain. The computer had targeted a landing site that looked acceptable from orbit. But as Eagle descended, Neil Armstrong saw something the computer couldn't: a field of boulders and craters directly below. Landing there risked tipping the module or damaging its legs. There was no time to send new calculations to Earth. Communication delays made that impossible, so Armstrong took manual control. He flew the lunar module sideways, searching for a safer patch of ground, while the fuel gauge dropped with every second. This wasn't cinematic heroics. It was trained decision-making under extreme pressure. The descent engine burned precious fuel that had no reserve. There was no second attempt. When Eagle finally touched down, the remaining fuel was measured in seconds, not minutes. Seconds. Had Armstrong hovered slightly longer, the engine would have shut down automatically and the module would have fallen. Mission Control knew it. The crew knew it. And then came the calm transmission. The Eagle has landed. Apollo 11 wasn't a smooth execution of a flawless plan. It was controlled survival, a chain of near failures managed just well enough to cross the line between disaster and history. Few things fuel doubt about the moon landing more than the photographs. They're sharp, well-framed, properly exposed, almost too perfect. When people imagine astronauts in bulky suits, thick gloves, harsh sunlight, and an alien landscape, they expect chaos, blurry images, bad angles, mistakes. Instead, the photos look deliberate, and that contrast triggers suspicion. But the photos don't look good by accident. They look good because they were engineered to. The cameras used on the moon were modified Hasselblad film cameras, stripped down to their essentials. No autofocus, no auto exposure, no unnecessary moving parts. The focus was preset to what photographers call the hyperfocal distance, meaning everything from a few meters away to infinity stayed in focus. Astronauts didn't need to adjust anything, they just pointed and shot. Exposure was also simplified. The moon has no atmosphere, no clouds, no haze. The sun is the only light source and its brightness doesn't fluctuate. Engineers calculated optimal exposure settings in advance, and the astronauts trained with those settings until they became instinctive. This wasn't casual photography, it was rehearsed, standardized and practiced repeatedly on Earth. The lighting itself confuses many people. Shadows appear sharp and objects in shadow remain visible. Some interpret this as evidence of studio lights. In reality, shadows are sharp because there's no atmosphere to scatter sunlight, and objects in shadow are visible because the lunar surface reflects light efficiently. Sunlight bounces off the ground and naturally illuminates nearby objects. Snow behaves the same way on Earth. Radiation is another common claim. Film is sensitive to radiation, so skeptics argue the images should have been destroyed, but radiation damage depends on dose and duration. The film wasn't exposed for long periods and was shielded inside the spacecraft most of the time. When examined today, the original negatives actually show tiny marks consistent with cosmic ray exposure, exactly what physics predicts. Finally, consider what faking these photos would require. Not one or two convincing images, but thousands, all consistent with lunar gravity, lighting geometry, astronaut movement, camera optics, and known physics, all surviving decades of analysis without a single definitive contradiction. The photos don't prove Apollo was easy, they prove it was prepared, and sometimes preparation looks so precise that people mistake it for fiction. Few things fuel skepticism about the moon landing more than the photographs. They're sharp, well composed, properly exposed, almost too good. When people imagine astronauts in bulky suits, thick gloves, and harsh lunar sunlight, they expect chaos, blurred shots, poor framing, blown-out highlights. Instead, the images look deliberate, almost professional, and that contrast triggers suspicion. But the photos don't look good by accident. They look good because they were engineered to. The cameras used on the moon were modified Hasselblad film cameras, stripped down to their essentials. No autofocus, no auto exposure, no unnecessary moving parts that could fail. The focus was preset to the hyperfocal distance, meaning everything from a few meters away to infinity stayed in focus automatically. Astronauts didn't need to adjust anything. They just pointed and shot. Exposure was also simplified. The moon has no atmosphere, no clouds, no haze, no scattered light. The sun is the only light source, and its brightness is brutally consistent. Engineers calculated the correct exposure settings in advance, and the astronauts trained with those exact settings until they became muscle memory. This wasn't casual photography. It was rehearsed, standardized, and drilled. Lighting confuses people too. Shadows look razor sharp, and objects in shadow are still visible. Some assume this means studio lights were used. In reality, shadows are sharp because there's no atmosphere to diffuse sunlight, and objects in shadow are visible because the lunar surface reflects light efficiently. Sunlight bounces off the ground and illuminates nearby objects naturally, just like snow does on Earth. Radiation is another common objection. Film is sensitive to radiation, so skeptics argue the images should have been ruined. But radiation damage depends on dose and duration. The film wasn't exposed for long periods and was stored inside the spacecraft most of the time. When examined today, the original negatives actually show tiny marks consistent with cosmic ray exposure, exactly what physics predicts. Finally, consider what faking these images would require. Not a few convincing photos, but thousands, all consistent with lunar gravity, lighting geometry, camera optics, astronaut movement, and decades of scrutiny without a single definitive contradiction. The photos don't prove Apollo was easy, they prove it was planned, and sometimes precision looks so clean that people mistake it for fiction. If there is one part of Apollo that truly feels impossible, it isn't the moon, it's the rocket. Saturn V was the most powerful machine ever built, 36 stories tall, 5 F1 engines at its base, each burning fuel so violently that engineers couldn't fully simulate the combustion in a lab. They didn't design those engines by elegant equations alone. They learned by blowing them up over and over until the metal finally held. Early tests failed constantly. Engines shook themselves apart. Fuel lines ruptured. Vibrations threatened to tear the rocket to pieces. One problem, later called pogo oscillation, caused violent longitudinal shaking that could have snapped the vehicle in half. Another miscalculation nearly destroyed the second stage during testing. These were not minor bugs. Any one of them could have ended the program. What made Saturn V work wasn't perfection. It was scale and obsession. At peak, over 400,000 people worked on Apollo across thousands of companies. Boeing built one stage, North American Aviation built another, IBM wrote software. Each piece was flawed in isolation. Reliability didn't come from simplicity, it came from relentless destructive testing. Engineers fired engines to failure on purpose. They overloaded structures. They treated hardware as expendable because knowledge was more valuable than parts. And when something broke, schedules didn't pause politely. They were crushed forward. Apollo didn't iterate like modern tech. It brute-forced progress with money, authority, and singular political focus. There was one goal, one deadline, and an acceptance that failure would happen, just not in flight. That mindset no longer exists at this scale. Today, systems are optimized for cost, efficiency, and long-term reuse. Testing is expensive. Failure is politically dangerous. Programs are spread thin, justified year by year, and designed to survive budget hearings, not existential races. Saturn V shouldn't have worked. It was too big, too violent, too rushed. And yet it did. 13 times in a row because it was built under conditions that no longer exist. The miracle wasn't the rocket's design, it was the coordination of an entire industrial civilization aimed at a single impossible task with permission to break anything that needed breaking to get there. When people ask why we haven't gone back to the moon, they often assume there must be a hidden reason. Lost technology, suppressed knowledge, a secret too dangerous to repeat. But the real answer is far less mysterious and far more uncomfortable. Apollo was never designed to last. It was a political sprint, not a sustainable exploration program. Its purpose was singular: demonstrate technological supremacy during the Cold War. Once that goal was achieved, the justification collapsed. There was no enemy left to race, no deadline forcing unlimited funding, no national urgency strong enough to override cost, risk, and public fatigue. The budgets tell the story. At its peak, Apollo consumed over 4% of the entire US federal budget. That level of investment would be unthinkable today, not because we lack the technology, but because we lack the consensus. Modern space programs must justify every dollar, minimize every risk, and survive constant political turnover. Apollo was allowed to burn money, accept danger, and move fast because it existed inside a moment of existential competition. Public interest faded too. The first landing was transcendent. The second was impressive. By the third, television ratings dropped. Walking on the moon became strangely normal, and without awe, the program lost its shield. Risk tolerance changed as well. Apollo accepted that astronauts might die. That wasn't hidden. It was understood. Today, a single fatal accident can halt a program for years. This isn't moral weakness, it's cultural evolution, but it means Apollo-style missions are incompatible with modern expectations. Michio Kaku often frames this not as a failure of courage or intelligence, but of alignment. Apollo feels impossible because it represents a rare moment when politics, funding, industry, science, and public belief pointed in the same direction. Briefly, we haven't gone back not because we can't, but because we no longer live in a world willing to act that way. Apollo wasn't a blueprint for the future. It was a historical peak, a glimpse of what humanity can do when everything else stops mattering. Apollo 11 doesn't feel impossible because it was fake. It feels impossible because it required a version of humanity that no longer exists. Total focus, total risk, and total commitment to a single goal. If this changed how you think about the moon landing, make sure to subscribe for more deep dives like this. And comment below, do you think humanity could still pull off something like Apollo today? Or was that moment truly a one-time peak?